example. We have 9 grams of water placed in a 2-liter industrial pressure cooker, and it's heated to 500 degrees Celsius. What is the pressure inside the container if no gas escapes? So a pressure cooker. A pressure cooker is a very strong, rigid container whose volume cannot change, but the walls are really thick so it can withstand the really big pressures inside of it. Good reason why. For example, water boils just under 100 degrees Celsius here. As water boils, as it is turning from liquid to gas, the temperature of it does not change. Whenever a material is changing phase, its temperature doesn't change. It will stay at that same constant temperature indefinitely.
Are you talking the temperature just before it boils?
It's whatever the boiling temperature happens to be, yes. So for us here, it's a little bit under 100 degrees Celsius. I don't know exactly the value off the top of our head.
And it's impossible to calculate.
It's impossible what?
Calculate.
To calculate. It is possible to calculate.
We did an experiment in the lab where we actually measured the temperature of boiling water.
Oh, did you? Cool. What was it? Do you remember?
I don't exactly what it was.
Okay. So,
95 or something.
around 95 degrees.
Exactly.
Let's play with 95 degrees. Let's say water does boil at 95 degrees Celsius for us. That means you're at home, you're cooking your spaghetti noodles or your ramen noodles, whatever you live off these days. When you turn the water on, when it gets to boiling, at 95 degrees Celsius, it will start to boil. It will continue to boil at 95 degrees Celsius until that water is completely and totally gone. Okay? It will not get any hotter than 95 degrees. Even if you make it boil really hard versus really soft, it's still 95 degrees. It doesn't change the temperature.
What about the gas?
The gas will be at 95 degrees Celsius as well. And as it expands into the room, it will start to cool off. Yes. Okay.
So why is there a difference between how fast it's boiling? So when it first barely starts to boil, you know?
Thermal mass? How fast?
It's how fast there's basically convection within the pan. You want to get full boil, meaning that all of the water is boiling in order to be uniformly throughout all of the water to be at the same temperature. But once all of the water is boiling, it will stay at that temperature. Okay? So when it's barely first starting, where you just see a couple bubbles coming up, that means the water at the bottom is at 95 degrees Celsius, but the rest of the water hasn't reached that point yet. It has to work its way through. Okay? Yes?
So what you're saying is as soon as the water reaches 95% of vapor, therefore you can't heat it past 95 degrees.
But you can heat vapor past 95 degrees.
You just can't heat water.
Right. Exactly. So basically, if we were to graph, well, never mind, because I can't think of what to put on both my axes. So anyway, the whole point of a pressure cooker is to increase the pressure, which increases the boiling point, the boiling temperature. So it makes things boil hotter. If you boil things hotter, you don't have to cook them as long, for example. Primarily, I've seen pressure cookers used primarily for, say, canning purposes, if you're going to can things. You need the temperature of the material, the water, whatever solution you have your veggies, whatever, in. You need the temperature of the water to get really hot to kill any sort of bacteria or any other bugs that might be in there. So you need to boil it at a higher temperature than you can just open to air. So that's primarily what I've seen a pressure for. I'm sure there's other reasons. But basically, you can boil and cook at a higher temperature with a pressure cooker. The volume of the pressure cooker will stay constant. The cooker itself is not designed to expand and get bigger. It's not designed to collapse and get smaller. So the volume will stay constant. So this would be an example of an isochoric process. So we're looking for the pressure in our container when the temperature is 500 degrees Celsius. We will be able to simply use the ideal gas law. We're looking for the pressure. We know the volume. We can certainly figure out the number of moles. R is a constant. Temperature, we know. So our pressure is simply going to be nRT over V. Now the number of moles. Number of moles is going to come from knowing we have 9 grams of water. Since water is H2O, oxygen is 16U, hydrogen's 1U, and there's 2 of them. So water, one water molecule is 18U, but that's the same thing as 18 grams per mole. The grams are going to cancel and leave us with moles. So if we have 9 grams of water, we have half a mole. So that's our N value. R is 8.31 joules per mole Kelvin. Temperature. Temperature has to be in Kelvin to cancel this Kelvin out in our gas constant units. 500 degrees Celsius plus 273, 773 Kelvin. Now, just as a side note, technically we don't use degree sign when we use Kelvin. It's not degrees Kelvin, it's just 773 Kelvin. Volume. In order for our units to work out correctly, our moles have canceled, our kelvins have canceled. Joules, remember, is a Newton times a meter. To get our pressure in newtons over meters squared, our volume will need to be in meters cubed. Turns out there's 1,000 liters in 1 cubic meter. So if I have 2 liters, I'm going to multiply by my conversion factor so that the liters will cancel. So basically, we have 0.002 cubic meters as our volume. So 1.61 times 10 to the 6th newtons over meter squared, or pascals. Remember, pascal is the same thing as Newton over meter squared. If you want it in ATM, you can divide by the conversion, the 101/300. This would be approximately 16 ATMs. So the ideal gas law is really quite handy, allowing us to relate pressure, volume, and temperature for a gas.